So we were at this setup where we were trying to, with this change of variable, to get the normal probabilities. So this is sort of a very generic concept. So this last calculation that we did in the last class. Let me try and build on that. So the concept I want to sort of illustrate is called change of variable. So change of variable. So here the idea is that from one random variable, if I do a transformation of it, how do I get the distribution of the second one? So so I will do this by examples. So this is probably a more relevant title. It's probably perhaps the following, that sorry, excuse me. It's called transformation of random variable. So let's do. I will do this whole concept by examples. Yes, I won't do it. So we'll illustrate this concept by example. Illustrate methodology via examples. Yes. Okay. So here's the first one. So let's say let's say x. Let me do the first example. Okay, how do I do this? I always get to this. Okay, here's the first example. So 5.3.1. So let's say I want to do x is uniform 0, 1. 0, 1. Y is equal to x squared. So how do I find density of that? So how do I find PDF of that? That's the first question. So now I know several things, right? I know the PDF of x. So I know f sub x of x is, let's say, is 1 over b minus a. B was 1, a was 0. So it's 1 by 1 minus 0. Then 0 is less than x less than 1, and 0 otherwise. This I know for x. Now I know my y is x squared. So how do I find the density function for y? So like we discussed last time in one of the previous classes, that okay, density function is important, but what connects the continuous and the discrete world was the distribution function. Right? So now what we'll do is, so what you do is, when you want to compute the PDF of a transformed random variable, the step one is, I'll always advise this, the step one is compute distribution function of x. So I want to get to y, okay, but I'll do this step by step. So once this step is what, that means the chance that, what is f sub x of x, the distribution function is same as x less than equal to x. So that's the same as minus infinity to x f of y dy. Okay. But that we know, we've done last time in one of the previous classes, that this was the same as 0 for x is less than equal to 0, was x when 0 less than x less than 1, and 1 if x is below equal to 1. That's how the distribution function looks. Okay. Net is a little slow today. Very nice. So now, once I have this, I have the distribution function of x. So the step 2 then is to compute distribution function of y. Okay, so now I want to compute the distribution function of y. So now what I do is I come down here. So this is the next step. So how does one do this? Here we know f sub y of little y is same as the chance that y is less than equal to y. But here what happens now? Here this is the same as the chance that x squared is less than equal to y. Right? Now once you have this step, you clearly observe the following. You have two things to do here. So how does one do this? So when you do this step, you go in two stages. So one is y is equal to x squared, right? That means 0 less than x less than 1, that's where the range of x is, will imply y squared, y equal to x squared will also be in 0, 1. So y also takes values in 0. So it means that the density function of y should be only supported in the interval 0. But anyway, let's try and see how to do this. So now first observation is if y is negative, the probability of, so let's go step by step. So y is negative, f sub y of little y is the same as the chance that y is less than equal to y is going to be equal to the chance that x squared is less than y. But that's going to be 0 because x is, if y is negative, so this is going to be equal to 0 because x squared can never be negative, so chance that x squared less than equal to y has to be equal to 0. So here you can use the fact that x squared is always non-negative, so probability x squared less than equal to y has to be equal to 0. That's just a fact. Now the next step is if y is non-negative. Okay, if y is non-negative, you have to be again a little careful now. Go fy less than equal to y. Is the change that fy of y is y less than equal to y. That's the same as the chance that x squared less than equal to y. But if x squared is less than y, that's the same as minus root y is less than equal to x is less than equal to y. That's what the expression gives you. But we already know that you can do it in many ways. So square root of y is positive. Square root of y is positive. I think the square root of y is positive. Right? You can do this calculation in many ways. You can first think of this as minus root y to square root of y, right, of f sub x of x dx, right? We know the density function is only positive in the positive half, right? So it's going to be equal to 0 to square root of y, right, of 1 of f sub x of x dx. Right? But in the negative part, the density function is 0. Right? Then once you have this, if you look at it, if you stare a little bit at this, it's just have to be careful how to do it. Right? So this is equal to, so if I can do it in many ways. So if you look at this expression right here, I can just tag along a minus infinity to root y, a minus infinity to 0, sorry. Maybe 0, then green, of 0 dx, right? Plus this person right here. Plus this person right here. Let me copy this. And now undo. So, that's easy to do. But since my density function is the same, I can write this as 0 to root minus infinity to root y. So density function matches. It's the same as f sub x of x. So this is from this definition. I'm using this property right here. This we call this as plus. So from plus. Here I've used property identification again. But this is what is this now? This is the same as f sub x of root y. That's the definition of that. So now we know what that is. So that is going to be equal to what now? So f sub x of root y, if you go look at this, let's call this as plus plus. We'll call this plus plus. In plus plus, what do we find? F sub x root y was 0 if root y is negative, but root y is positive. So it's going to be root y. This is from plus plus. It's going to be root y when 0 less than y less than 1, and 1 when y is bigger than equal. And let's look at this calculation right here. For negative, we already know it's equal to 0. Let's call these a star now. So star and double star will give you the entire distribution function of that. So therefore, from star and double star, we get that f sub y of y is equal to, let me erase the little bit, f sub y of y is the same as 0 when y is less than or equal to 0, root y when 0 less than y less than 1, and 1 when y is bigger than 20. Now the last step in this to finish calculation is step 3 is you compute the density function. Compute density function, the probability. So how does one do this? Density function is, how do you do density function? Now we know this, use the important fact. Use the important fact that if you have a distribution function, you differentiate it in y, f dot prime is going to be equal to f of y, right? So you have to use this property. Let's call this triple star or triple plus property also. So that uses the property. So now that means clearly immediately you get the fact that the density function f of little y is the derivative. The derivative of f we know is clearly 0 if y is less than 0, and also 0 when y is above 1, because the function is constant. And inside this, the derivative of root y is just 1/2 square root of y. Right? That's just easy to see, right? That we know this d by dy of y to the 1/2 is 1/2 square root of y. That's just the factor. So now we have a PDF of this. It's 1 over square root 2y, 0 less than y less than 1, and 0 outside. So this is the standard formula procedure. So let me just do a split view, and so you can see the whole thing in one shot. So I move the whole page here. So this is what I would always recommend while doing transformations. You compute the distribution function of one random variable, that original one that you're interested in. From that, you compute the distribution function of the transformed random variable y, and then differentiate to compute the density function of the transformed variable. So this is what I would recommend. We're always doing k variable. So the let's just sort of let me just go back and just recap the thing. So let me just get this back to 100%. The idea is that we change a variable, set up the methodology, and we do is we go via distribution functions or variables. and then use the relationship between PMF or PDF to distribution. And the key thing was that the distribution function was a canonical concept for both discrete and continuous. Of course, here I'm doing only continuous random variables, but in general, so we will do only continuous. In the discrete world, you can do directly. You can do PMF directly by transformation. But in the continuous world, you go to distribution function and then come to the density function. Right. So we already saw this thing about random. Let's just do another example. I like this example a lot. This is example 5.3.4. Here, what one does is the following. You take two parallel lines. Okay? So y equal to 0 and y equal to 1 on R2. So y equal to 0 and y equal to 1. So let's say, let me draw the axis. The axis, let me draw it in blue. So blue axis here. This is the axis. The axis is here. And this is the origin. So then what I do is, let's say someone is standing at the origin, and let's say she chooses an angle theta. Okay, so choose an angle theta uniformly in 0 to pi. So in 0 to pi, I choose an angle. So let's say I choose an angle theta. So, and then I drop a line. Okay, so angle theta. So now, so what I do is you choose an angle theta, uniformly from 0 to pi, right? And then you drop a line segment. So draw a line segment. From 0, 0 to the line y equal to 1. Okay, that's what you do. Now you call this point where you hit it, you call it as x. So this point is x comma 1. Okay. So let's say this is what you do first, then you say point hit by segment is x comma 1. Now I want you to find the distribution of x. Find the PDF of x. So the idea is clear. So I have two line segments y equal to 1, y equal to 0. I choose an angle between 0 and pi uniformly. I drop a line segment to the line y equal to 1, and I want to find the distribution of x, or in some sense, PDF of x. Of course, I've been a little glib here. So of course now x is an element in R, and it is a continuous random variable. Right? So that's something we have not established, but that's something that's kind of obvious from the picture. Right? So, because x can be any point on the line y equal to 1. Right? So now I have an angle theta. So now how do I do this? So now again we do step by step, right? So first thing you observe is in the example that so the first observation is, what's the first observation? X should be a function of theta. Right? So how do you find x now, the function of theta? Let me use a different color. Let's see if I can find that color. Let me do some pink. Maybe I'm going to pink. Let me do pink. So how do I find x? X is this line. If I drop this line right here, if I want to find my x, x is just I can look at the top guy is kind of easier. X is just tangent of 90 minus. So observe that x is a transformation, and the transformation is x is just tangent of pi by 2 minus 3. Right? So this is the first observation you make. So once you have this, you're on your way, right? You know the x is a function of what, of theta, and then you can do steps before, as before. So what is step one? Step one was find distribution function of theta. So what is that? So now theta is uniform 0 pi, right? So we know already from the previous example that f sub, let's say capital theta of, let's say little y is going to be equal to 0 if 0 is less than or equal to y or less than or equal to 0 is going to be equal to let me call it as okay, 0 less than y, so minus infinity less than y less than pi is 1 over pi minus 0, or no, it's going to be just pi. It's going to be just pi, right? That's a distribution function. It's going to be linear, it's not 0. And then it's going to be 1 if y is bigger than 0. Right? Let's see if I missed it. Let's see. So x minus a by b minus a. It's going to be 1 over y over pi when 0 is in. That's the density function, distribution function of theta. What's step 2 now? Step 2 we discussed was to find the distribution function of x. Of x. What's that going to be? That's going to be the same as of x. That's the same as f sub x of little x is the same as the chance that x is less than or equal to x. But what's x? X is just tangent of this one. So you can think of x theta as so the same as the probability. So the same as we go down, we go step by step. So the same as if I want to compute, we go to black. Same as the probability. So if x less than or equal to x is same as the tangent, right, of pi by 2 minus theta is less than or equal to x. But that's the same as what now? That's the same as pi by 2 minus theta is less than or equal to the arc tangent of x. Right. Next step, and that's the same as the chance that if you do the algebra properly, is same as theta is at least pi by 2 minus arc tangent of x. Now you can use axioms of probability to say the same as 1 minus the chance that theta is less than pi by 2 minus arc tangent of x. Theta is a continuous random variable, so less than or less than equal doesn't matter. So same as 1 minus the chance that f sub theta is like pi by 2 minus at the point pi. So now we are in business now, right? So first thing you observe is that this person here, right? So x is in R. If x is in R, the angle pi by 2 minus arc tangent, first arc tangent x is always going to be between 0 and pi. This is a fact from trigonometry that we know. So arc tangent x is between minus pi by 2 to pi by 2. Pi by 2 minus that is always be 0 and pi. So this will imply that for any x in R, this is 1 minus from, let's call this as, let me call it notation, maybe this one as, let's call it as dagger, let's say. So from dagger, I know that this is the same as 1 minus, whatever that is pi, 1 over pi, and what is y? Y is pi by 2 minus arc tangent x. That's what I had, right? F of y was y by pi. Here my y was pi by 2 minus arc tangent x, and that if I do algebra is just same as 1/2 plus arc tangent of x divided by pi. Very nice. So that's a distribution function of x. So x in R, we have come to this. What are the last? This for any? This is true for any x in R. That's how the function is. What's the last step? In step 3 was to compute the density function. Compute the probability density function of x. So that's what we do. You just use the fact that you differentiate it to say fx prime at this is same as f sub x. So that's what going to be. So little f sub x at x. All you have to differentiate this guy. If you differentiate this person, half is 0. Arc tangent is 1 over 1 plus x squared. So you get 1 by 1 plus x squared for x in. This is kind of an interesting density function. Came out of this example. So that completes this picture. And x is typically known as what's called Cauchy distribution. With I think the parameters here are it's supposed to be 1 and 0, 1. So Cauchy 0, 1. I'll explain the general one some other time. So x is suppose x got a name. It's called Cauchy distribution. And the idea again is that x again is like kind of normal, but it's a little different. So it's again it's like 1 over pi here, and then comes down this way and comes down this way. But somehow the tails are different. So tails are not like normal. So it's not like normal. I mean, it is symmetric, but in the sense that decay is not like normal. Because in the normal you have exponential decay. So let me do a split view and sort of recap the example. So what I did was I just a simple thing. I said, okay, fine. I'm going to start with 2 lines, y equal to 1 and y equal to 0. I shoot a line across from angle at an angle theta. I hit the top line at y equal to 1 at point x, and I want to find the distribution of x. And the way I do that, again, I can do my 3-step algorithm: distribution function of theta, function of x, and PDF of x. Very nice. Okay, I'll stop here for this slide, and then we'll try and do more transformation next time and close this topic.